Hello, everyone. So in this first lecture for Math 115, College Algebra, we're basically going to review factoring. In particular, we want to review how to factor polynomials. And the reason why is we'll need that later when we are solving quadratic equations. We will have to be able to factor. So in this section, we're going to first go over something called prime factorization of a number. I'll remind you guys how to do that. How to find the lowest common multiple of a set of numbers, how to find the greatest common factor of a set of numbers, and then we'll review how to factor polynomials. Okay, so first, remember what the prime numbers are, right? Remember, they're numbers that are only divisible by themselves and 1. So 2 is the only even prime number. So 2 is a prime number. And then 3, 5, 7, 11, so on, right? These are the numbers only divisible by themselves and 1. The numbers that are not prime are called composite numbers. So those are all the ones like in between. So like 4, like these are divisible by other things other than themselves and 1. 6, 8, so you're filling in all the gaps here, right? 10, 12, and so on. And then you might notice here I didn't list the number 1. The number 1 is sort of a special number, sometimes called a unit. It's neither prime nor composite. We don't really deal with the number 1. Okay, here is the interesting thing. It turns out that any composite number can be written as a product of prime numbers. So that means any number can be written as a prime number, right? Either it's already prime or it can be written as a product of prime numbers. So this is what we call the prime factorization. And it's unique, ignoring the order, right? The order of the factors could be different, but the same factors will be there, right? So the same product of factors will always equal that number. So to remind you guys how to do the prime factorization, let's do a couple of examples here. So let me start with the prime factorization of 48. So I think the best way to do this is to do a tree. So I'm going to write 48. And then I'm going to branch off of the 48. And the way I like to do this is I always like to, on the left-hand side, find the lowest prime number that will go into the number I'm trying to factor. So again, remember that the prime numbers are 2, 3, 5, 7, and so on. So ask yourself, does 2 go into 48 evenly? Yeah, it goes in 24 times, right? 48 is even, so 2 definitely goes into it. It goes into it 24 times. Then I branch off of the 24. And I ask myself, does 2, let me start with 2 again, does 2 go into 24? Yep, it goes in 12 times. Then I branch off to 12. Does 2 go into 12? Yeah, it goes in 6 times. And then finally, does 2 go into 6? Yes, it goes in 3 times. And you're going to stop when all these numbers on the left-hand side are prime numbers, right? And the last one, both of them should be prime. So therefore, we've shown that 48 factors into 2 times 2 times 2 times 2 times 3. Another way of writing that is you could write this as 2 to the 4th power, right? So remember that means multiply 2 by 2 by 2 by itself 4 times, and then times 3. And if you want to explicitly put an exponent, I'll put a 1 there. So 2 to the 4 times 3 to the 1. That's what 48 factors into. Now, another way you could do this, and you may have learned different ways to do this, is to find larger factors that equal 48 to start with. Like, so instead of using the lowest prime number, you could just find 2 factors that give you 48. For example, like 6 times 8, right, gives me 48. Then I need to branch off the 6 and branch off the 8. So 6 is 2 times 3, and then 8 would be 2 times 4, and then branch off the 4, 2 times 2. And notice here, you're going to get the same factors. right? You have 4 2's and 1 3. So it's 2 to the 4 times 3 to the 1. This is fine. This method is fine. I like this method better just because it's cleaner. Like sometimes when you use this method over here, it can get really messy just trying to find all those factors by branching off using the tree. So I tend to like this method better, but either one works. Okay, let's do another example. Find the prime factorization of 360. So I'll start with 360. I'll branch off. Does 2 go into 360? Yeah. It goes in, was that 180, I guess? 180, right? Does 2 go into 180? Yep, it goes in 90 times. Does 2 go into 90? Yeah, it goes in 45 times. Does 2 go into 45? No, it doesn't. So now work your way up to the next prime number. Does 3 go into 45? Yeah. 3 goes into 45 15 times. Does 3 go into 15? Yep. 3 goes into 15 5 times. And notice now I stop because I have all prime numbers, right? So in this case, it's going to be 2 times 2 times 2 times 3 times 3 times 5. Right, so 360 will be 2 times 2 times 2 times 3 times 3 times 5. And then I could write that as 2 to the third times 3 squared times 5 to the 1. So that would be the prime factorization of 360. Okay. Let me go to the next page here. So now that we reviewed prime factorization, let's talk about how to find the lowest common multiple of a pair of numbers or a set of numbers. It could be 2, it could be more than 2 numbers. So first of all, what is the definition of lowest common multiple? Remember, it's the smallest number that's a multiple of the original numbers. In other words, it's the smallest number that divides the original numbers evenly. So for example, let's say we want to find the lowest common multiple of 15 and 20. So first thing you could do is you could write out, we actually don't want to solve the problem this way, but this sort of illustrates like what it means to be the lowest common multiple. So you could write out all of the multiples of 15, right? So what does that mean? If I take 15 times 1, right, I get 15. That's a multiple of 15. Then 15 times 2, you're just multiplying by every whole number here. 15 times 2 gives me 30. 15 times 3 is 45. 15 times 4 is 60. So 15, 30, 45, 60, 75. These are all multiples of 15. I do the same thing with 20, right? So 20 times 1 is 20. 20 times 2 is 40. Times 3 is 60. Times 4 is 80, and so on. 100, 120. These are all multiples of 20. So what's the lowest common multiple? So what number is common to both and it's the lowest common multiple? Well, in this case, it's going to be, it's already circled here, the 60 and the 60, right? So you could say that the lowest common multiple of 15 and 20 is equal to 60. Okay, it's the smallest number that divides both of them evenly. All right. So again, when you're actually asked to solve a problem like this, you don't actually want to use this method. It will just take too long. So there's a technique that we can use that involves prime factorization. That's why I reviewed prime factorization. Let's talk about that. Bring this up here. So for instance, let's find the lowest common multiple, we'll do this example 3 here, of 20 and 45. So the first thing you should do is you need to find the prime factorization of both numbers. So I want to find the prime factorization of 20. So let me branch off. So I have 2 times 10, 2 times 5. And I can write this as 2 times 2 times 5, or 2 squared times 5 to the 1. Let me do the same thing for 45. So 45 So 2 doesn't go in, but 3 goes in, right? 3 goes in 15 times, and then 3 goes into 15 5 times. So I can write this as 3 times 3 times 5, or 3 squared times 5 to the 1. Okay, now usually what you want to do is you want to make these factorizations symmetrical. Okay, you don't have to do this, but I think sometimes this is a nice way of doing this. So what does that mean? Well, notice I have 2's and 5's in the first factorization, right, of the 20. I have 3's and 5's in the second factorization. I like to have 2 3's and 5's in both of these factorizations. So how do I do that? Well, I could put in a 3 in the first factorization if I write it as 3 to the 0 power. Why does that work? Because remember, anything to the 0 power right over here is equal to 1 by definition. Okay, so I'm not changing what that product is, but I'm including that factor of 3 in there that I wanted. Okay, so that still will give us 20, right? But it has 2's, 3's, and 5's in it. Now, same thing for the 45. I need to put a 2 in there, so let me write it as 2 to the 0 times 3 squared times 5 to the 1. Okay, so now they have the same factors, right? So now, to find the lowest common multiple, what you do is you take each factor the greatest number of times it occurs in either of the factorizations. So if I look at the 2's, I have 2 to the 3, right? I have 2 to the 3, I have 2 to the 0. So what's the largest one? Well, 2 to the 3 is, right? Basically, you're just looking for the largest exponent. 3 is larger than 0, right? 8 is larger than 1. So I'm going to take this factorization for the 2's. For the 3, if I look at the 3, I have 3 to the 0, I have 3 squared. Well, 3 squared is larger, right? So I'm going to keep track of these. So I want to find the lowest common multiple of 20 and 45. So I took 2 cubed, that was the largest one for the 2's. For the 3's, I have 3 squared. And then the 5's happen to be equal, right? 5 to the 1, 5 to the 1. So I just take, one of them, it's the same. So I can write this as 5 to the 1. And then if you multiply that out, so this is 8 times 9 times 5, that is going to be the lowest common multiple. Okay, and I think that's, 360, I believe, right? So this is, I'll do it as 40 times 9. Yeah, this is 360. So 360 is going to be the lowest common multiple of 20 and 45. It's the smallest number that 20 and 45 will go into evenly. Okay, so that's the process, and you'll get more practice. All right, that was the lowest common multiple. Now let's review greatest common factor. So the greatest common factor of 2 or more numbers is the largest factor that is common to all the numbers. The largest number that each can divide by evenly, or the largest number that, each can divide by evenly. So for example, the factors of 15 and 20 are, let me go to the next page here. So if I write out all the possible factors of 15, right? Usually the way you do this is you start with 1 times what will give me 15, 1 times 15. Then I try 2. No, 2 doesn't go in. I try 3. 3 times 5 gives me 15. And then 4 doesn't work. And then 5, I'd start repeating myself, right? So I can stop there, and I know that 1, 3, 5, and 15 are factors of 15. I do the same thing with 20. So 1 times 20 gives me 20. I try 2. 2 times 10. Yep, that's 20. Try 3. Note that doesn't work. Go to 4. 4 times 5. And if I go to 5, I start repeating again, right? So I can stop. So therefore, all these numbers, the 1, the 2, the 4, the 5, the 10, and the 20 are factors of 20. Okay, they're not prime factors, they're just factors in general. So what's the greatest common factor to both 15 and 20? Well, what's the largest factor that's common to both? It's the 5. Right? So we say that the greatest common factor of 15 and 20 is equal to 5. Okay, so again, you don't actually want to work it out this way. You could, but if you have larger numbers, this could take a while. So the best way to do this is to use prime factorization again. So in this example, we want to find the greatest common factor of 100, right? To do that, I'm going to start by finding the prime factorization of 180 separately again. Okay, so let's do that first. So I'm going to have 100. This is 2 times 50, 2 times 25, and then 5 times 5. So I can write this as 2 times 2 times 5 times 5, or if you want, you could write it as 2 squared times 5 squared. And then 80 is going to factor into 2 times 40, 2 times 20, 2 times 10, and then 2 times 5. So I can write this as 2 to the 4th times 5 to the 1. Okay, and both factorizations have 2's and 5's in them already, right? I don't have to add anything to the 0 power to match it. It's already symmetrical. Okay, so how do I find the greatest common factor of 180? Well, remember, for lowest common multiple, we took each factor, right, either the 2's or the 5's, the greatest number of times, right, with the largest exponent that it occurred, and we found the product. For the greatest common factor, it's the opposite. We take each factor the least number of times it occurs, and we find the product. So if I look at the 2's here, now I want the 2 with the smallest exponent. So I want 2 squared, and then I want the 5 with the smallest exponent, so I have 5 squared in the first one and 5 to the 1, so I want 5 to the 1. And if I multiply that out, that's 4 times 5, which is 20. So 20 is the greatest common factor of 180, right? It's the largest number that goes into both of them evenly. Okay, so again, hopefully you guys that came back, hopefully you've seen that at some point in the past. Here, let's do one more. Let's find, so using prime factorization, let's find the greatest common factor of 15x cubed and 45x squared, because we're going to start needing to factor variables as well, right? When we talk about polynomials and basic expressions. So let's do the tree again on the 15. So this is, well, 2 doesn't work, right? So I try 3 is the next prime number. It goes in 5 times, and I can stop, right? 3 times 5. But remember what x cubed means. X cubed just means, it means x times x times x, right? So I can write this as 3 to the 1 times 5 to the 1 times x to the 3rd. Do the same thing with 45. Right, so I'll find the prime factorization. So 2 doesn't work, 3 goes in 15 times, and then 3 goes in 5 times. And then x squared is just x times x. So this is going to be 3 squared times 5 times, and then I could write it as x times x, or I'll just leave it as the exponent form, x squared. Okay, so I want the greatest common factor, right? So therefore, I want each factor, the 3, the 5, and the x, notice it's symmetrical right now, the least number of times it occurs. So if you look at the 3's, I have 3 to the 1 and 3 squared. So I'm going to take this one, right, the 3 to the 1. So it's 3 to the 1. And if I look at the 5's, they're the same, 5 to the 1, 5 to the 1. So the least is still going to be 5 to the 1. And then the x's, I have x cubed and x squared, so the 2 is smaller, so I want the smallest one, so x squared. And if I multiply that, it's 15x squared. So that's going to be the greatest common factor of 15x cubed and 45x squared. Okay? Why do we need that? Because later, here, I'll do sort of an example of what we'll see in the future. Let's say you have an expression, 15x cubed plus 45x squared, and you want to factor that expression. Then the first thing you should look for is what is the greatest common factor of that expression that you can take out from both terms. And we just found it's 15x squared, right? So if I pull out a 15x squared, I'm left with x, right? Because if I multiply this back out, if I distribute this back in, 15x squared times x, I'm going to get my original 15x cubed. And then what's the second term? Plus, and I'm left with, I guess, a 3, right? The other way to see this is if you, let me do it over here. If I take 15x cubed, right? I'm factoring out a 15x squared. So that's sort of like divided by 15x squared. And if you divide that, right, 15's cancel, x cubed over x squared is going to give you just an x to the 1, right? So I'm left with just an x here. And then if I do 45x squared divided by 15x squared, I'm factoring out the 15x squared. The x squares cancel, and 45 divided by 15 is going to be 3. That's why I'm left with the 3 here. Okay, so that's why we need this, because we're going to need it. We always want to look for the greatest common factor of a polynomial to factor out first. Okay, so now that we've done that, let's start looking at actual expressions. And again, you should always look first to see if there's a factor, the greatest common factor that you can factor out of the expression to begin with. So for this first one, it says factor 12x minus 4. So we could actually do the trees on all of these, right? And let me do it for this first one. So I have 12, that's 2 times 6. 6 is 2 times 3. And I have an x, so I can write this as 2 squared times 3 to the 1 times x to the 1. And then 4 is 2 times 2. So this is 2 squared. And again, if I want to be symmetrical, I can write a 3 here as long as I write it as 3 to the 0, right? Because then it's just really a factor of 1. And I can write an x here if I write it as x to the 0. So what's the greatest common factor of 12x and, I have an x here, right? Of 12x and 4? Well, I take each factor the least number of times, right? The 2 squared, they're the same, so I can just take it 2 squared. That is the least. 3 to the 1, 3 to the 0, so now I really want 3 to the 0. X to the 1, x to the 0, so I want x to the 0. So this is equal to 4. Remember, these are just 1s, right? Times 1 times 1. Anything to the 0 power is 1. So the greatest common factor is 4. That's what I need to factor out. And you probably saw that. I mean, with smaller numbers, you can just do this in your head, right? You can look at this and say, what's the largest thing I can factor out of both of these? Well, a 4 is. Okay, and if you need to do it formally, you could also do it formally. So we take out the 4, and what are we left with? So 4 times what will give me the original 12x? Well, I'm missing a 3x, okay? Or again, the other way of doing it is if you divide 12x by 4, right? Whatever you're factoring out, that's what you divide by, and that will give you what's remaining, so which is 3x. I like to think about it as 4 times what? If I multiply it back, right? If I FOIL it back out or distribute it back in, what will give me the 12x? Well, I'm missing a 3x. And then 4 times what will give me a minus 4? Well, I'm missing a negative 1, right? Because 4 times negative 1 will give me a negative 4. So that's it. So 12x minus 4 just factors to 4 times 3x minus 1. Okay, let's do some more of these. So what about this next one here? I want to factor 9x cubed plus 3x plus 6. It looks like, so x is not common to every term, right? So it looks like maybe just a 3 is common to every term. So I can pull out a 3, and then what am I left with? I'm left with 3x cubed plus 3 times what will give me 3x, so I'm missing an x, and then 3 times what will give me a 6, I'm missing a 2. Okay, and then that's as far as we're going to go. This is a cubic. This is probably hard to factor here, and maybe not factorable, so I'll just leave it like that. All right, next one. 39x to the 4th minus 13x squared. It turns out actually that 39, if we factor this, right, 2 doesn't go in, but 3 goes in, and how many times it goes? It goes in 13, right? And 13 is a prime number. Okay, so this first one is basically 3 to the 1 times 13 to the 1 times x to the 4th. And then the second factor is going to be 13 to the 1 times x squared. If I want to put a 3 in there, I can put it as 3 to the 0. So if I want to find the greatest common factor, I take each of these the least number of times, right, the smallest exponent. So I want the 3 to the 0, that's the 1, 13 to the 1, and an x squared. So this is just 1 times 13 times x squared. This is 13x squared. So that's the largest thing that we can take out, right, of both those terms. So I remove the 13x squared, and I'm left with 3x squared, right? Remember, let me remind you of that. If you multiply two powers, like x to the a times x to the b, the rule is you keep the base and you add the exponents together, right? So x squared times x squared is going to be x to the 2 plus 2, which is 4, right? So if I distribute this back in, x squared times x squared would be x to the 4th here. And then I need a negative, and then again, it looks like it's just a 1, right? If I multiply 13x squared times negative 1, that gives me the negative 13x squared. So that would be the factorization of that. I'm just pulling out the greatest common factor of each term. Okay, what about this one? Let's see if we can do this just by looking at it. It looks like 3, right? 3 goes into all these numbers. So I can pull out a 3. And then what's the smallest x? It looks like x to the 1, right? Because there's x squared, x cubed, so I want the smallest one, x to the 1. So pull on x. And then it looks like for the y's, it's going to be y squared, right? I have y cubed, y squared, so I'm going to pull out a y squared. And then I'm left with what? I need a 2, right, to give me the 6. I need an x squared. So if I do x times x squared, that'll give me x cubed. And then y squared times y will give me y cubed. Plus, then I'm missing a 15, right? Because 3 times 15 will give me 45. I'm missing another x. And then y squared times 1 is y squared, so I don't need to do anything with the y's. And then plus 7, right? 3 times 7. The x is okay, and the y squared is okay, right? Just a 7. So that would be it. That would be the greatest common factor would be 3xy squared. Okay, so now let's look at some trinomial expressions. Basically, these are polynomials that have 3 terms, and we're going to focus on this case right here, where the leading coefficient, in other words, the coefficient of the x squared term is a 1. So if there's nothing in front, right, there's always a 1 there. It's 1 times x squared. Normally, in general, this would be ax squared plus bx plus c. But we're going to focus on the case where a is 1, right? That's the easier case. So to factor these, if they're factorable, sometimes they're not factorable, but if they're factorable, we use what's called the BC method. And the way we do this is we look for two numbers that when multiplied will give us C, and when added will give us B. Okay, this is only true if you have a 1 here. If the leading coefficient is a 1, the A is a 1. Then you can look for two numbers which multiply to give you C and add to give you B. Okay, so to start, let's just, without even looking at a polynomial expression, let's see, can we come up with two numbers that multiply to give us 48 and add to give us 16? So what are some factors of 48? Well, I could do like 1 times 48. That does not add to 16 though, right? I could do 2 times 24. That doesn't add to 16. I could do, 3 times 16, I think, is 48? Yeah, 3 times 16. But that doesn't add to 16. 4 times 12. That will actually add to 16, right? So this doesn't work, because that would be like 49. This doesn't work. That's 26. This doesn't work. That's 19. But this actually does work. That would be 16. So the two numbers that I would be looking for in this case would be 4 and 12, right? They multiply to give me 48 and they add to give me 16. Okay? So once you have those, and actually this next example illustrates this with those particular numbers. So if I want to factor this, I'm going to end up with, if it's factorable, I'm going to end up with two factors. The only way to get the x squared is if I have an x and an x as the first term of each of those factors. Okay, we'll check this later by FOIL. You may remember that acronym FOIL, where we multiply first, outer, inner, last. So we can expand this back out to see if we get the original expression here. So how do I figure out these two numbers? Well, here's where I'm looking for two numbers. When multiplied, give me C, give me 48, and added, give me the B term, positive 16. Well, we just found those, right? It's positive 4 and positive 12. And it doesn't matter what order I put them in, so I'll just write the positive 4 first, and then the 12 over here. Okay, how do I check to see if this is correct? So this should be the correct factorization, x plus 4 times x plus 12, right? We factored that expression. To check it, I can multiply it back out. Right? I can expand this back out, and that's what we typically call FOIL. So how do I expand it back out? Well, I multiply the first terms. Let me remind you of the acronym FOIL. So this is first, this is outer or outside, let's call it outer, inner is the I, and last. It's just to remind you, right? It's an acronym here. Or really it's a mnemonic to remind you how to do this. So the first, x times x gives me x squared. X times 12, I can write as 12x. 4 times x is positive 4x. And then positive 4 times 12 is 48. And notice that the x's are like terms, so we can combine them. What's 12x plus 4x? Well, that's going to be 16x. And that is the original expression, right? So that is the correct factorization. So you can always check it by expanding it back out. Okay, let's try a few more examples here. So I want to factor x squared minus x minus 12. So again, this is a nice case where I have a 1 as the coefficient of the x squared term, the a. So immediately I can write the two factors here into parentheses, and I know that the x squared can only come from x times x. Okay, then I want to think of two things when multiplied give me negative 12. Don't forget about the sign there, that's important. And then added give me what? Well, remember, if there's nothing there, there's really a 1 there, right? There's always a 1 there. So they need to add to give me negative 1. So if you think of all the things that give you negative 12, right? You could have negative 12 times positive 1. You could have positive 12 times negative 1. But if you multiply those, right, you get negative 12. But if you add them, you definitely don't get negative 1. But if you keep going here, let's see, 3 times negative 4. I could have negative 3 times positive 4. I guess this one works, right? If I multiply positive 3 times negative 4, I'll write the positive there, I get negative 12. And if I add 3 plus negative 4, that gives me negative 1. So that's what I want. So one of these factors will be positive 3, and the other one will be negative 4. Okay, and again, you could check it by foiling it back out, right? If you multiply that back out, you're going to get x squared minus x minus 12. Okay, what about this one? So I'll do x times x. Now I want two things. Well, multiplied will give me positive 6, and added will give me negative 5. So it looks like they both must be negative, right? If I multiply two negatives, I get a positive because I need to add them to get a negative. So it's going to have to be two negative values. And it looks like negative 2 and negative 3 will work, right? If I multiply those together, I get positive 6. If I add them, right, take away $2, I take away another $3, I've lost $5. I get negative 5 if I add them together. So those are the two values I want, negative 2, negative 3. And that'll work. And then this one, well, we should always look first. So there's definitely not a 1 there, right, in front of the x squared term. But is there a greatest common factor that I can factor out of each term first, right? That's what we first looked at earlier. We should do that if we can, right? So in this case, yeah, a 4 is common to every term there. So I can factor out a 4, and I'm left with x squared minus 3x minus 10. And now this piece, right, is a trinomial where there's basically just a 1 there, right, in front. So we can factor that, or we can try and factor that. So let's see if we can factor that. Well, I know if it's going to be factorable. Again, sometimes you can't do this, and then you just say it's not factorable. But in this case, let's try it. So I have x squared is x times x. I want two things in multiplied will give me a negative 10, and when added will give me a negative 3. So when multiplied, give me a negative 10, and added will give me a negative 3. So like I could do like positive 10, negative 1. That does not add to negative 3, right? I could do, and then eventually you're going to hit upon, what about negative 5 and positive 2? If I multiply, I get negative 10. And if I add them, I get negative 3. So that works. So one of these is going to be negative 5. And the other one's going to be positive 2. Okay, so now the final factorization then would be 4. Don't forget that 4 there. And then you're going to have x minus 5 times x plus 2. Okay, what if we have a trinomial where the a is not a 1, right? So we have a more general ax squared plus bx plus c that we want to factor. If that's the case, then we could try something, sometimes people call this the AC technique, where what you do is you multiply the a and the c. So it's the coefficient of the x squared term and the constant. You multiply them together, and then you try to find two numbers that when you multiply them give you that number AC, and when added give you b again, the middle number b. And then if you can find those two numbers, then you can use what's called factoring by grouping. Okay, so let's this is best explained by doing an example here. So let me go to the next page. And let's try these. So in this case, right, the a is not a 1, right? I don't have a 1 in front of the x squared term. I have a 2. So let's try this AC method. So I'm going to multiply 2 times 9. So positive 2 times 9, that's going to be 18. Right, and multiply the a times the c, including the signs here. Now I want to try and think of two things that multiplied give me positive 18 and added give me positive 9. Give me the middle term to 9 there. Well, I can do that, right? Again, you can try a bunch of things like 18 times 1, but that does not add to 9. If I do 2 times 9, that doesn't work. But what about 3 times 6? That works, right? Positive 3 times positive 6. So they multiply to give me 18, and they add to give me the middle number 9. All right, once you find those two numbers, what you do now is you rewrite that middle term, the linear term, the x term, in terms of these two factors here. So I can rewrite this as 2x squared plus, now the 9x I'm going to write as 3x plus 6x. And then I still have the 9 here. So this is really the same as 9x. I just rewrote it in a slightly different way. All right, why do I do that? Because now I can use what's called factoring by grouping, right? If I have four terms here now, I want to factor by grouping. So what you do is, let me erase this bottom one. What you do is you group the first two terms, you group the last two terms. And if I focus just on the first two terms, I want to factor out the largest thing I can from those first two terms. Well, it looks like the thing that's common to both is an x, right? I can factor out an x, and I'm left with 2x plus 3. Okay, then I look at the second group. I want to factor out the largest thing I can to hopefully be left with this term, to be left with the same 2x plus 3. Can I do that? Yeah, if I factor out, I want to be left with that, right? That'll work if I factor out a positive 3, right? Because 3 times 2x is 6x. I can check it, right? 3 times 2x is 6x, and 3 times positive 3 is positive 9. Notice that these two terms are the same here. So I can factor them out, right? It's sort of like saying this. If I had, say, x, I'm going to call that whole term, the 2x plus 3, I'm going to call it a. And then I have plus 3 times a. See how the a is common to both terms? I can factor it out, and I'm left with x plus 3, right? I'd have a, that whole expression, times x plus 3. So in this case, I'm going to factor out that expression, pull it all the way out front, and I'm left with x plus 3. So that would be the correct factorization. But by the way, you could also factor it out at the end and be left with x plus 3 as the first term, right? It doesn't matter. The order doesn't matter of those factors. But usually you pull it all the way out front and you leave it like this. All right, so let's try some more of these. This AC method, which really involves factoring by grouping. So again, I don't have a 1, right, in front of the x squared term. So let me multiply 5 times negative 6. That's going to give me negative 30. Are there two things that multiplied that give me negative 30 that add to give me the middle term, plus positive 7? Yeah. Again, if you think about this for a little while, if you have a positive 10 times a negative 3, right, that'll give me negative 30. And if I add those, I'm going to get a positive 7. So I'm going to rewrite that 7x in terms of these two factors here. So I'll write it as a 10x minus 3x. Okay, now I want to group. Now actually, when I group this, sometimes what I do is, because I have a negative here a negative here, I don't want to like, I want to emphasize that it's like plus a negative 3x. So what I do is I sometimes just put in a plus there. Then I group these terms together. And now we do what we normally do, right? I look at the first group. Is there something I can factor out that's common to both terms? Yeah, it looks like a 5x, right, is common to both terms. So I can pull out a 5x, and I'm left with x plus 2. Now, I like to be left with an x plus 2 for the second grouping. Is there something I can pull out? Yeah, if I pull out a negative 3, so I take out negative 3, I'm left with x. And a negative 3 times what gives me negative 6? Positive 2. That's exactly what I wanted, right? Remember, I want these to match here. So now, since they match, I can factor them out front. And I'm left with 5x minus 3. So that would be the correct factorization. Okay, in this one I have a 4 and a negative 6, right? So that's going to be negative 24. I want two things that multiply to give me negative 24 that add to give me negative 5. Let's see. 24 and 1, there's no way I can get it, right? 12 and 2, that won't work. What about 4 and 4 and 6? Oh, 3 and 8, right? Will work? Okay, so if I do positive 3 and negative 8, yeah, that'll multiply to give me negative 24 and add to give me negative 5. Right, because I want these to add to give me the b term, right? The middle term, negative 5, the coefficient of the x. Okay, so I'm going to rewrite this again. By the way, it doesn't matter what order you put these in. I could write it as 3x minus 8x or minus 8x plus 3x. It doesn't matter. It's all going to come out to be the same anyways. Just for variety, let me write it as minus 8x plus 3x. Right, so I rewrote that middle term in terms of the two factors we just found. Minus 6. Okay, so now I group. What's the largest thing I can pull out of the first term? Well, I can take out a 4x, and I'm left with x minus 2. And then for the second one, I can factor out a 3, and I'm left with x minus 2. Great, so that these match now, so I can pull out the x minus 2's all the way out front, and I'm left with 4x plus 3. So that would be the factorization. Okay, the next one. What if you have? So notice that this is not a quadratic expression. It's a cubic. There's a cube term here, right? A 3. So there's no like easy way. There's no like AC method or whatever we can use. But sometimes, and for this class, if you're given like an expression that has 4 terms like this, just try factoring by grouping, because it may work. It may be successful. Okay, and the examples that we give you, right? If we give you 4 terms, it probably will be factorable if you use factor by grouping. So let's try factoring by grouping here. So we're going to try, so 4 terms, we're going to try factoring by grouping. Okay, so I want to, again, because I have a minus here, I'm going to write a plus in front of it. Just so when I group now, I really have to recognize it's plus a negative 9x, right? I don't want you to think you're multiplying it, you're adding. So now, what can I factor out of the first term? Well, I can take out an x squared, and I'm left with x minus 2. Okay, is there something I can factor out of the second term so that I'm left with an x minus 2? Yeah, actually, if I pull out a negative 9, I'm left with an x, and a negative 9 times what will give me positive 18? A negative 2, right? So I'm left with x minus 2. And now, since x minus 2 is common to both terms, I can pull it out front, and I'm left with x squared minus 9. Okay, It turns out that this expression here can be further factored, okay? We're going to talk about that in a second as like one of the special cases, but let me just remind you of it right now. If you have an expression that has the form a squared minus b squared, this is factorable into a plus b times a minus b. You can prove this by foiling this back out, right? You're going to get a squared minus ab plus ab. They're going to cancel, and then minus b squared. So I get the original a squared minus b squared. So this term right here, this can be written as something squared, right? In fact, it's x squared minus 3 squared, right? 9 can be written as 3 squared. So the a is like the x in this case, and the b is the 3 in this case. So this factors into a plus b times a minus b, right? So then I can rewrite this expression, the x minus 2 I still have there, and then the x squared minus 9 I can write as x plus 3 times x minus 3. Oops, minus 3. So that would be the factorization of that expression. Okay, again, this has 4 terms, so let's just try factoring by grouping. So if I group the first 2 terms, and then the last 2 terms, what can I factor out of the first group? Well, it looks like I could take out a 2x, right? It's commentable terms. And I'm left with a y minus 1. Can I somehow get a y minus 1 from if I factor something out of the second group? Yeah, if I factor out a positive 3, I'm left with a y minus 1. So now the y minus 1 is commentable, so I can pull it out front. And I'm left with 2x plus 3. Okay, so sometimes grouping will work. I mean, in most cases it actually won't work, but for the examples that we give you in this class, typically if you have 4 terms, grouping will work. Okay, what about these special cases? So the first one here I've kind of already mentioned. The difference, and I think this one is a good one to remember. So the difference of 2 squares, if you have something squared, like a squared minus something else squared minus b squared, that always factors into a plus b times a minus b. Okay? If you don't want to do that, you could use the techniques that we learned here, because this is like saying, here, let's look at this first example here. I have 9x squared. There's no x term, right? So you can think of that as 0 times x, right? The b is 0 in this case, minus 25. So we could use the techniques that we learned earlier, right? I could use the AC method. So I want 2 things when multiplied. Well, actually, first, before that, start by multiplying a times c, right? So 9 times negative 25 is going to be, what is that going to be? Negative 225. And then I want 2 things when multiplied will give me negative 225, and added will give me 0, right? Because the b is really 0 in this case. And actually, it turns out that positive 15 and minus 15 will work. Okay, so then I can rewrite that middle term as positive 15x minus 15x minus 25. And again, I'll put a plus there to remind me that I'm adding the negative 15x. Then I'm going to factor by grouping, right? So I group the first 2, group the last 2. So what's the largest thing I can factor out of the first group is a 3x. And I'm left with 3x, because 3x times 3x is 9x squared, plus 5, right? 3x times 5 would give me 15x. And I'd like to be left with a 3x plus 5 in the second group. Well, if I factor out a negative 5, then I'll end up with positive 3x and then positive 5. So now I can factor the 3x plus 5 out completely out front, and I'm left with 3x minus 5. So you could use our usual techniques, right, of, in this case, the AC method. But it's much quicker by using this special form, the difference of two squares. If you recognize that 9x squared is the same thing as 3x squared, again, to remind you of that, right, if I have something, let's say I have x, y to a power, right? I'll say 2. Then this is the same thing as x squared times y squared, right? Each one gets raised to that power when you expand that out. So 3x squared would be 3 squared times x squared, which is 9x squared. And then 25 is also a perfect square. It's the same thing as 5 squared. So now I have this form, right? I have this form ax squared minus bx squared, where a is 3x and b is 5. So this factors into a plus b, so 3x plus 5, and then a minus b, 3x minus 5. Okay, so notice we'll get the, if you check, it's the same, right? This is the same as what we got over here. But it's much quicker if you recognize that that is a difference of squares. Okay, this one actually, you could do, again, using the AC rule, but this is a lot more complicated. So this one, hopefully you would just recognize that it's a difference of squares. So 16x to the 4th can be thought of as 4x squared all squared, right? Because that'd be the same thing as 4 squared times x squared squared. I have to remind you guys of some of the rules for exponents, right? If I have x to the a raised to the b, the rule is you multiply the exponents together. So x squared squared would be x to the 2 times 2, which is x to the 4th. Okay, you have to remember some of those rules of like exponents. And then 81y to the 4th can be written as 9y squared squared, right? Because that will be 9 squared, that's your 81, and then y squared would be y to the 4th. So I can write, so this is really a difference of squares, right? I can write this as 4x squared squared minus 9y squared squared. So this is my a, this is like my a, and this is like my b. So this is going to be a plus b times a minus b. Right, so that would be the correct factorization for that. Okay, and then the other special case is if you have something called a perfect square trinomial. So remember, trinomial is like 3 terms, and it turns out that if you have this form, a squared plus 2ab plus b squared, this factors into a plus b squared, right? A plus b times a plus b. And if you have a negative here, if you have a squared minus 2ab plus b squared, it factors into a minus b squared. To me, this is hard sometimes to recognize these forms. Again, if you don't remember that, right? If you don't recognize the form, then you can just use the usual rules, like the AC rule, and it'll work. Okay, but sometimes it could be quicker if you recognize this form here. So like in this first example, where I have 25x squared plus 20x plus 4. It turns out that this actually has that first form there, right? If I can write 25x squared as 5x all squared. I can write 20, actually let me do the 4 first. I can write the 4 as 2 squared. And then I can write the 20x as 5x times 2 times 2. Again, see, I think sometimes this is hard to recognize, but so in this case, the A is our 5x, the B is our 2, and then if you notice here, this term is like 2 times A times B, right? So really the 20x has that form 2 times A times B. So this original expression I could write as 5x squared plus 2 times A times B plus B squared. And we know that it's going to factor into A plus B times itself, right? Which we can just write as squared. Okay, but again, I think that's hard to recognize. So the way I would solve this problem is I would just do the regular AC rule, right? So if I here let's do it that way and make sure we get the same answer here. So if I multiply, I'll do it over here. 25 times 4, that gives me 100. Can I think of two things to multiply, give me 100, and add to give me 20? Yeah, 10 and 10, right? So this is 10, positive 10, positive 10. So I can rewrite that middle term as 10x plus 10x. Now I'm going to factor by grouping. What's the largest thing I can take out of the first term? Well, I could take out a 5x. And I'm left with 5x plus 2. What's the largest thing I can take out of the second one? Well, I can take out a 2, and I'll be left with 5x plus 2. So the 5x plus 2 is common, so I can factor it all the way out front. And notice I'm left with 5x, also 5x plus 2. Well, since it's the same thing multiplied together, I could write this as 5x plus 2 squared. Okay, so factoring using the AC method will always work. And for me, at least, I think it's easier than trying to recognize that it has this special form here. Okay, same thing for this last example. So this right here turns out to have this form, right? If A is 7x and B is 1, because 1 squared gives me 1, then it turns out that 2 times 7x times 1 gives me negative 14x. So it has this form here. So this would factor into A minus B squared. But if that's hard to recognize, which again it is for me, I would just use the AC rule. So to use the AC rule, we can multiply 49 times 1. That gives us 49. I want two things to multiply, give me 49, and added give me negative 14. So let's see. Oh, I guess a negative 7, right? If I multiply negative 7 times negative 7, that's positive 49. If I add them, I get negative 14x. So let me write out that expression again, but using these factors of negative 7. I'm going to put a plus here just to remind myself. Now I'll factor by grouping. So what's the largest thing I can take out of the first term? Well, I can take out a 7x, and I'm left with a 7x minus 1. And then what's the largest thing I can take out of the second one? I would ideally want to be left with a 7x minus 1. Well, notice you can get that if you factor out a negative 1, right? Because then if I multiply this back in, negative 1 times 7x will give me negative 7x. Negative 1 times negative 1 will give me positive 1. So notice this 7x minus 1 is common, so I'll pull it all the way out front. And I'm left with also 7x minus 1. Well, this is really 7x minus 1 squared. Okay, so it did have that form, but it was actually easier just to use the AC method in this case, and that will always work. Okay, great. So hopefully that reminded you of how to factor, basically factoring the different types of trinomials mostly in this case. Great, thank you.